To understand how computers work today, look at the machines that started it all. Since the days of these massive tape drives, the core logic has remained the same. Information is processed sequentially as a long string of ones and zeros. Over the decades, engineers made those ones and zeros smaller, packing billions of transistors onto tiny silicon squares. But we are now pushing against the physical limits of the universe. Transistors are becoming so small that electrons jump across them, breaking the binary logic. Instead of a classical bit confined to 1 or 0, we have a quantum bit, or qubit. It exists in superposition, holding 0, 1, or both simultaneously. By holding all states at once, it calculates millions of distinct possibilities at the exact same time. This architecture bypasses the limitations of traditional silicon. It allows engineers to solve problems that would take current supercomputers thousands of years to finish. That processing scale is already attracting industries dealing with complex variables. Researchers are actively looking to use quantum systems to model battery materials, optimize logistics grids, and simulate the molecular folding required to discover new drugs. But the math that makes it easy to simulate a complex molecule also makes it easy to factor large prime numbers. That poses a problem because factoring large primes is the mathematical foundation of modern cryptography. The codes protecting bank accounts, routing private messages, and securing national secrets could be solved by a mature quantum computer in minutes. This reality has split the tech sector into two distinct camps. On one side, engineering firms are racing to build a stable, functional quantum computer. On the other, cybersecurity specialists are developing new encryption methods to protect the world's data from those very machines. The next decade will be defined by this tension. We are watching the development of new processing capabilities alongside the erosion of current information security. Engineering a machine that relies on quantum mechanics is difficult because qubits are fragile. The slightest vibration or temperature change causes them to lose state. To solve this, companies are taking radically different physical approaches. Hardware firms like Rigetti and D-Wave rely on superconducting circuits. They construct specialized multi-chip processors and place them inside cooling chandeliers that drop the temperature to near absolute zero to keep the system stable. Xanadu takes a different route, using a photonic approach. Instead of freezing metal circuits, they use particles of light, photons, traveling through optical fiber. Because light doesn't easily enter its environment, these systems can compute at room temperature and network with standard telecom cables. Then you have companies like Inflection and IonQ focusing on atomic architecture. They suspend neutral atoms and trapped ions using lasers and magnetic fields, manipulating the atoms themselves to perform calculations and build precise sensors. Regardless of how the hardware is built, these companies share a common business model. They offer quantum computing as a service, or QCaaS. Instead of buying a multi-million-dollar machine, corporate and government clients rent access to these processors over the cloud to run their own experiments. Whoever successfully scales their specific physical method first will dictate the architectural standard for global supercomputing. But as those physical machines scale up, so does the risk. If a functional quantum computer is controlled by a malicious state actor, every piece of encrypted information currently traversing the internet becomes exposed. The timeline for this threat is active. Intelligence agencies warn of harvest now, decrypt later. Hackers are stealing massive volumes of encrypted data, stockpiling it in vaults, waiting for quantum processors to catch up and derive the cryptographic keys. To combat this, cybersecurity firms are building post-quantum defenses. Arcit, for example, develops cryptographically agile software solutions. They focus on securing data in transit over networks without forcing clients to replace their physical hardware. In the financial sector, BTQ Technologies provides a specific defense. They built the quantum-secure stablecoin settlement network, which protects digital asset ledgers, tokenized deposits, and the core transaction infrastructure of major commercial banks. At the hardware level, companies like SealSquaw are engineering new post-quantum semiconductors. They are embedding quantum-resistant cryptography directly into the physical microchips that power devices, authentication tokens, and industrial control systems. Adding longer passwords or thicker firewalls will no longer work. To secure the digital economy, these defenders have to rewrite the underlying mathematics of cryptography before the hardware catches up. What began as theoretical physics in academic laboratories is now a highly capitalized, publicly traded ecosystem. This graph charts the projected path. High error rates drop over time, entering a stable, fault-tolerant zone. Here lies the foundation for software. Platforms like Xanadu's PennyLane and Inflection's Superstack let developers test applications today, ready for tomorrow's hardware. The entire sector is locked in a duality. Billions of dollars are flowing into the pursuit of raw computational speed, while equal effort is spent preparing a defense of the world's protected information. Over the next decade, the ultimate victor won't be a single engineering team that constructs the fastest processor. It will be the broader ecosystem of builders and defenders that can successfully harness that power without breaking the digital world in the process.